Hey, this is Tara Schaller, and this is a video demo of my project Machine Learning Breakout. This was a capstone project for my Oregon State Bachelor's of Science in Computer Science. I completed this project with two other engineers, Joel Huffman and Jeff Dickinson. The purpose of this project was to use the Unity game engine to build a game that includes an AI opponent, and we trained that opponent using the ML Agents toolkit. So first I'm going to just walk you through the game, and then we'll walk through the code and talk about some issues in development. So first off, playing the game, we started up here in the Unity since we're in the game engine here, we're just running it through here. So you can see this is just kind of our little demo screen. There is some music in the background. I hope that's not too distracting. So this is just our little intro screen. You can see there's a how to play section, some sound options. Let's see what happens if we turn. You can hear the music there. The screen recording is interfering with the music. If you download the executable, it sounds real nice. There's an exit option, of course. When you hit play, you go to a level select scene. You've got level 1, level 2, level 3. So going to level 1, I get these errors on my Mac. They don't happen on a Windows, on the Windows version. So you probably, if you ever played Atari, you remember how Breakout works. You've got a paddle at the bottom that bounces the ball back, and you use the ball to break the bricks. The red ball on the left is the human player, and the blue ball on the right is the AI opponent. And as you can see, that AI opponent is doing a great job at breaking those bricks over there. We trained it really well. So you can just play this game, and it keeps track of points and lives, and eventually I'll just lose on purpose here. You can see that AI wins. Yay. You have options like replay the level or go to the main menu. We can go back to the main menu. So that is the game. And I apologize for that noise in the background. When you play the game on Windows, the sound is much nicer. So I'll walk you through some of the code here that I was lucky enough to work on. So a big contribution to the gameplay itself, I wrote the code for the bricks. It needs to check for collisions, and of course, if it, not all bricks break on the first collision, so it counts down the number of collisions, and when the brick is basically done, worn out, it has to destroy it. And we're keeping count of the bricks and decrementing the count of the bricks also. And of course, the bricks change color as they break down. So also I contributed to the initial version of the game manager in the first stage of the development. In the final stage, it was obsolete, but it was used throughout about 60% of the development. This is the paddle agent that runs our intelligent AI opponent. We worked on this together in a mob programming session to set it up to adapt some examples we had to work in our game. The most important function here is this agent action that controls the actions of the intelligent agent, and this vector action contains arrays of integers that basically encode the possible actions. And so the actions for our agent were to release the ball or hold it, and of course movement, which would be left, move right, or hold still. So a little bit about training the game. So training the agent. So this is where I felt like my biggest contribution came in. The overall idea of the project I felt like I contributed a lot to the overall idea of the project. My team members wanted to do some really complicated stuff that I didn't feel like we could accomplish in the time limit that we had. So I suggested that we do a really simple game, like the simplest possible game I could think of, which was this Atari Breakout game. And use the game data, the information from the game engine as observations for the learning agent. And so we trained the AI opponent with a deep reinforcement learning algorithm called Proximal Policy Optimization that basically works just like you would train a dog or a dolphin or the way you would think to train something. You provide rewards for desirable behaviors and penalties for undesirable behaviors. And the agent it tries a whole combination of all the possible actions it can take and tries to maximize its overall total reward. So for example, here in agent action, we have an add reward ball held penalty. So here we're penalizing the agent for holding on to the ball too long, because if you don't do that, it just sits there and holds the ball. So the way to get it to force it to release the ball is to add a little penalty. Down here, collecting observations. This comes in during training. And these are the possible observations that the agent can use that are an input to try and figure out what it's doing. So its observations were the paddle position, the ball position, a vector representing the movement of the ball, and whether or not it was actually holding on to the ball. And then over here, also in brick, you've got where's the line? Okay, so if you break a brick, this code right here, if a brick is broken, it is giving the agent a small reward during training. So the workflow for using the ML Agents toolkit is basically you build a game, then you run TensorFlow in a separate Python process. That Python process communicates with the Unity game engine, and it runs the training process. The results of that training process are saved as a neural net. And here I'll click over to it so that you can actually see it. So the results of the training in the Python process are saved in a file, a neural net model, and you can actually just click and drag that into your slot. You can try, this is kind of cool, you can try several different training methods and just click and drag the one you like into the Unity editor. And then once it's trained, you re-embed it into your game. So a significant obstacle we encountered during building this was initially we had the game set up and we had the training academy set up. We thought we had all of our code correct, but for whatever reason, when we were running the training, the agent refused to train. The paddle just zipped over to the right-hand side of the screen and it sat there holding onto the ball and it wouldn't do anything. So after carefully going through the documentation and the examples, I discovered the problem was not with any of the code we had, but with conceptual setup of the training. So the key spot was right here under vector action. That controls the possible actions that the paddle could take. And branch size was the key. We had, when it wasn't training, we had 1 and 2 here, which meant that we weren't giving the intelligent agent the option it didn't have enough possible actions. It didn't have an action to release the ball, and it never had an opportunity to move left. So that explained why our training was going crazy. And once I changed these branch sizes and tweaked the code a little bit to give it the ability to move left. Then training started, and from there it went pretty well. So once again, that was trained with deep reinforcement learning and proximal policy optimization using the Unity game engine and the ML Agents toolkit. So thank you very much, and thanks for checking in.